All right, let's get started. So today we're going to continue our discussion of security over a network, and we'll talk about certificates today at length, which came up in last lecture on TLS. And in particular, we'll talk about certificates integrate with TLS to provide HTTPS in the web browser, which is a secure connection from the browser to the backend web server. So just to remind you guys, the sort of context or the sort of TLS protocol we were talking about last lecture is used, of course, by the browser to connect to websites. So if you have your browser running on your computer and you go to some URL like https amazon.com, then what your browser is going to do is open a TLS connection to the web server at amazon.com, looking up the name in DNS. And it's going to speak the TLS protocol. We talked about it last time. So it's going to send maybe the name, amazon.com, wants to connect there. And then Amazon is going to provide back the public key of the server. And the server, of course, has this public key, but also the secret key needed to participate in the protocol. And then the client will send the encryption of some session key. And then we'll actually start communicating encrypted with the session key over this channel. So this should seem familiar from last time. And the focus of this lecture is all on this problem of key distribution. Namely, how does the client know that this public key is the right one for Amazon? So this is typically called key distribution. And oftentimes in cryptographic protocols, distributing the keys is often, or usually even the hardest part of the protocol. So here, we need to know that when our browser connects to some server, this is the correct public key that we're seeing on the wire. The only sort of goal the browser had in mind was connecting to this URL, doesn't know what the public key is, or what necessarily to expect, so we need to somehow help the browser along. And this is where certificates came into play. We talked about them briefly last time, but we're going to spend this whole lecture on certificates and certificate authorities. Make sense? Any questions so far? All right. So let's talk about what a certificate authority is and what it does for us. So certificate authority is going to be some server out there on the internet whose job is going to be to connect the name that the browser wants to connect to, like amazon.com, to a public key that we can then use to bootstrap all the cryptographic security over the network. So if we have this CA, it's going to be some entity with a server probably, and it's going to have this table of registered public keys, names and public keys. So it might be that Amazon registers with this CA, so there's an entity, amazon.com, has a particular public key, PKS, and maybe MIT.edu has another public key in this table. And this CA server is going to help our web browser determine if it's talking to the right server or not. And it's going to be important that this certificate authority has its own secret key with a public key corresponding to it. And the browser is going to know this thing. It's going to know the public key of the certificate authority. And whenever the server wants to convince the client that it's using the right public key, it's going to use a certificate. So what a certificate is, this hopefully looks somewhat familiar from last time, is going to be a signature by the certificate authority using its secret key of a statement that basically says amazon.com is this particular public key. So the CA is going to take this row in the table, generate this certificate. It's going to go up here to our server. We'll talk about, I guess, how this happens out of band. And then eventually the server is going to include it in this message over here as a way to convince the client. So the client is going to look at the cert and connect the dots, starting from the public key that the client knows about. It's going to check this signature in the certificate. It's going to check that this public key is the right one, and so on. So this hopefully looks all familiar enough. Make sense? Questions? So one thing I wanted to do today quickly is do a demo. This whole stuff is real in the website. So we can look at, for example, the certificate of the website I run for this class. So in the browser, you can actually pull up the certificate. So just double check, actually, this URL, it's an HTTPS URL, which means that the browser is actually speaking this protocol to my web server here. And in the browser, we can pull up the certificate information for this web server. And there's quite a bit of stuff, actually, in the certificate that we haven't talked about explicitly. But there's if you drill down into sort of the fields of the certificate, one thing that's particularly important is, of course, the public key here's the public key. Let's scroll down here. Here's the 2048-bit RSA public key of my web server. It's in the certificate. And also in this certificate is the name of my web server, css.ccl.mit.edu. So that's sort of the main fields. It's the name and the public key, along with lots of other fields, expiration dates, revocation information, who issued it, etc. But quite a bit of stuff. We'll talk about some of this in a bit. But this stuff is real. Your browser is checking this. We can also look at sort of the UI of the browser. So if you're going to an HTTPS site, you get this nice little icon. If you go to a HTTP-only site, like the question site we have for you guys, it's an HTTP URL, not HTTPS. The browser actually tells us it's not secure. So these days, like it used to be the case, the browser would not have anything for regular HTTP sites and would have like this fancy lock for HTTPS sites. Now it's basically reversed. You get this not secure indication that you shouldn't trust this website at all, except for sort of questions that don't matter. So that's sort of the cert side. You can also look at actually all the CAs that are in your browser. If you haven't looked at this before, it's kind of interesting to look at. Let me find where this is. Certificates in the security side. You can actually pull up all the certificate authorities that your browser knows about. So here's the authority list. There's a lot of them. Like here's the ones that start with A. Here's the one that start with B, C, China Financial Certs, Komodo, DigiCert, DigiNotar. There's a lot of cert authorities out there. And this is basically just a bunch of list of public keys. So you can pull up any one of them, for instance. You can view it. And the main details that matter is really there's going to be a public key in here. Subject's public key. And this is the 2000-bit RSA public key of this particular certificate authority. So the browser has probably about 150 of these certificate authorities that it trusts to sign certificates for checking HTTPS websites. Does this make sense? This is roughly what's going on in your browser. Questions about this? All right. Good. So let's talk about, I guess, exactly how these certificates flow around. So we sort of sketched out some diagrams so far. But there's really sort of two important steps to sort of the certificate plan. And they're sort of all connected by this website in the middle. So Amazon.com, for instance, is the server that wants to use HTTPS for its users that visit its site. So the first thing it, of course, needs to do is talk to the certificate authority and register itself. So there's a secret key and a public key of the certificate authority. That sort of starts out being baked into the browser somehow. And in order for Amazon.com to participate in HTTPS, it actually has to first generate its own key. So Amazon needs to run keygen in order to produce its secret key for the server and a public key for the server. And it never gives anyone the secret key, which is kind of one of the cool things about using public key crypto here, which is that the certificate authority can register these public keys, but the certificate authority never sees the secret keys here. So once Amazon.com generates this public key, it's going to send some kind of a request to the CA saying, I want to register, and here's my public key PKS, and my name is Amazon.com. And there's probably going to be some proof that goes along with this request that proves that it's actually Amazon.com and not an adversary trying to impersonate Amazon. And then the CA is going to basically add this name and public key to the stable, logically speaking, Amazon.com, there's a public key, and send back the signed certificate that the server asked for. And now, once the certificate has been handed out to the server. Now the server can keep giving it to clients as many times as it need be. So the cool thing here is that the certificate authority is actually not on the critical path. We don't actually have to talk to the certificate authority from the browser. We can just have the server hand out this pre-signed message whenever someone wants to connect to the server. So for the CA interaction, this proof is important. So we'll talk about how this happens a little bit later. So the CA needs to be convinced that this is really Amazon. And from the browser side, there's also a bunch of checks that need to happen for the browser to trust or accept this certificate from Amazon.com. So one of the sort of biggest questions is the browser has to do is decide whether the name actually matches. So the browser was trying to go to Amazon.com. Did it get a certificate for that name? So this is crucial. This is what's going to connect what the user is expecting in the browser, namely the Amazon.com page, to some cryptographic guarantees from the CA over the network. So the browser critically needs to check that the name matches what the user is expecting. Then, of course, we have to check whether this is a trusted CA. Was the certificate actually signed by one of those couple of hundred CAs that we looked at in the browser? Or is this like some CA that's not actually trusted by this client? Of course, it actually has to check the signature, whether it's properly signed. And there's a couple of other fields in the certificate. One of the maybe more important ones is that certificates tend to have an expiration date, among other things, in the signed message, which is meant to indicate that the certificate should only be accepted for a certain period of time, typically on the order of a couple of months or a year. So the browser needs to check if the certificate is not expired. The reason for expiration dates, of course, is to sort of bound the damage if some key is compromised or if a name is transferred. These certificates are only valid for a certain amount of time, and at least they'll expire after a year. We'll get back to this point as well. But anyway, so the browser needs to sort of check all these things, that the cert looks valid, and if everything matches up, then it's going to display this nice lock icon or whatever secure indicator in your browser to say that you're actually looking at the right website. Does this make sense? This is the browser sort of, implementing what you would sort of expect, I guess, from these certificates and speaking TLS. Question? Yeah, I see. So your question is, okay, so sort of, what can Amazon know about this client browser in turn? And like we've been mostly talking about the browser authenticating Amazon. So there are sort of two maybe parts to this answer. One is you're saying, well, maybe Amazon doesn't want to support certain browsers because they tend to be related to fraud in some way. So, in principle, yeah, Amazon could look at the user agent string or other properties of the browser and say, well, you're using Firefox. I don't like that browser. Please switch to something else to purchase Amazon items. They don't do this, but, it's available to them if they wanted to. I think one reason why this HTTPS interaction is so focused on authenticating servers is that servers already have ways of authenticating users using passwords or single sign-on or email addresses, things like that. So the server already has some way to figure out who the user is, but we need, but there, at least typically, isn't a similar way for the user to authenticate the server. Partly, well, one way to think of it is that actually, when you have a password shared with a site like Amazon, you can actually use it to authenticate both ways. The server could use the password to authenticate you. In principle, you could also use the password to authenticate the server. It's like, well, prove to me that you know my password. And there's actually cryptographic protocols that do this. Based on a password, both sides can authenticate each other. But the reason this is not super widely used is that user accounts typically sort of are done on top of the web instead of as part of the web. What I mean by this is that you typically go to Amazon's website before you even have an account. And in order to do this, you need to be able to authenticate Amazon before you have an account. Then you create an account there. So somehow the way things have worked out, and also because of the web wanting to support many kinds of sort of styles of user sign-in and account credentials, they're sort of done on top of the browser instead of being baked into the protocol, like MIT client certs for Touchstone, etc. They're sort of a way for the browser to actually also present a cert to the server, not super widely used. Yeah? Yeah. So it's super important. So one thing, just to say, your question is in this chain of validation, what's going on here? One thing I wanted to point out before getting to the name question, it's not necessarily in this order. These are all things that have to be checked. Probably you're going to check the signature first, then you see if it's a good CA or something like this. But the name, this is the critical thing. There's two names going on here. One is the name inside of the certificate. So the certificate is going to talk about some name, like Amazon.com is PKS. This certificate better be talking about the name, or some name. And the other name you're going to cross-check it with is the URL you are trying to go to. Like the browser might be trying to load HTTPS Amazon.com. That's the tab that you're sort of loading up. It better match this name. Because if I was trying to go to Amazon.com, I talk to a server, it gives me a perfectly valid search for MIT.edu. It's not what I'm expecting. Maybe MIT is a perfectly good site in some other context, but if I want to go to Amazon.com, I shouldn't be seeing MIT's website. And could be much more damaging if MIT was like adversary.com. Adversary has a valid search for their name, but it has to be matched with the site that the user is trying to go to. So that's what I mean by name matches. So it has to be the case that, Question? So there are extensions to certificates that allow certificates to say this cert is valid for all names under this subdomain. So you can have wildcard certs. So maybe star.amazon.com, meaning it'll match anything to Amazon.com. But it's very restricted. Either an exact match or it's like a fancy cert that says it's a wildcard thing, and then it's you can match that wildcard, but it's then only a suffix star.something.com. Yeah. Uh-huh. Mm-hmm. Yep. So to rephrase the question, so what happens with the cert? This sign check, this is calling the verify function that we looked at in last lecture. So this check is that we can actually call verify, and this thing is properly cryptographically signed. And then whether the name matches, that's not a cryptographic thing at all. There's just some message inside the certificate that talks about a particular name, and then we're going to look at the name. It better be the same name we're expecting. Make sense? Good. Other questions? All right. So let's talk about how certificates are actually going to help us here. And if you recall, certificates are really important in the context of active attacks, where an adversary actually impersonates someone or modifies network messages. If our network is sort of passively adversarial to us, meaning it'll correctly deliver messages that are just snooping on our messages, we don't actually need certificates. We don't need this whole certificate authority plan if the adversary isn't going to intercept our network messages. But if we have these man-in-the-middle or MITM attacks, then let's just walk through the various scenarios that can happen to convince ourselves that certificates really do solve the problem. So what you should think about is that we have a browser out there on the internet, and it wants to connect to some site, let's say Amazon.com, but when the browser goes to connect, an adversary intercepts the connection. And you actually end up connecting to the adversary's server. And this might be because of some network attack, could be because the adversary intercepted DNS requests, who knows. And at this point, the adversary has to supply some public key and certificate. Remember that in TLS, the adversary has to supply a public key and a certificate that goes with that public key. So the adversary has a couple of options here, right? So the adversary could supply a public key of the adversary, but, the adversary has the corresponding secret key. But in that case, now they have to cook up a certificate. So how does the adversary do this? Well, a couple of things they could do. They could give us a cert for the real Amazon.com. So the adversary could get the cert for Amazon.com and just supply it, but give its own public key. Well, in that case, what's going to mismatch is that the public key sent over the wire to the client doesn't match the public key that's inside the cert. So the browser is going to reject this and says, well, you gave me one public key, but the cert actually tells me to use something else. This is not correct. So that's going to reject this kind of attack. Another thing that the adversary could do is maybe send a cert for PK adversary, but now the name is going to be attacker.com. So the adversary can easily get a certificate in their own name. But now this name check is going to fail. The adversary can get a correct cert for their public key under their name, but the browser is going to say, well, that's not the site I was trying to go to. It's going to also reject this connection. I guess another thing the adversary could do is also specify their key and sign their own cert, signed by, adversary CA. They can sign their own certificate with their public key, but now this is not going to work because this is not one of the CA public keys that the browser is expecting. It's not the list of 150 we looked at in the browser that are allowed to sign certs. So this attack also doesn't work out. And then, of course, one thing the adversary can do is send the real public key of Amazon and the real cert of Amazon. That'll work out, but now the adversary can't decrypt those messages because they don't have the corresponding secret key. So hopefully this, this is not a complete enumeration of all the things the adversary could do, but hopefully this builds up some intuition of why all these checks are important, because they're going to foil various attempts by the adversary to sort of impersonate the server. And the only thing that's going to work out for the adversary is supplying the real Amazon server key with a real cert, and then the adversary can't decrypt. Hopefully makes some sense. Questions? Yeah? Okay, so your question is, what about this attack? So, it's true. If the adversary really is one of those 150 CAs, or if one of those 150 CAs basically delegated their key to the adversary, then, yeah, this doesn't work out. So this sort of falls under the category of the CAs are compromised, if you will. So we'll talk about that a bit. But you're absolutely right. This sort of assumes that the adversary isn't one of those 150 CAs we talked about, and isn't sort of closely related to them. Okay, so is there scoping? That's a legit question, and would have been a sensible design to have scoping, but no. So the way that this certificate scheme works in browsers today is that pretty much all those 150 CAs we looked at are completely global. Any one of them can sign any name to key mapping, and the browsers will trust it. And there's something you were alluding to, which is like a CA delegating something. So CAs can actually sign other keys, and they don't necessarily need to be keys for Amazon.com. They could be like a sub-key over another CA. So it might be that like one of those root CAs signs a key saying, oh, here's another CA, I'll sign it. I'll let the CA decide who else to sign later. So it's possible, and there's actually many more CAs than in that list that are delegated. But yeah, here we're talking about the situation where let's assume the adversary isn't a CA themselves. That would make our life more difficult here. Other questions? Concerns? Yeah. Yeah, so I guess let's talk about what kinds of attacks aren't covered in this, right? So attacks despite certs. And probably a pretty prominent threat vector, used to be the case, maybe still is to some degree, is maybe the user just uses HTTP and not HTTPS. And this is sort of the SSL strip attack you're referring to. So what's going on here is that if I were to type in some URL into my browser, like let's say I type in foo.com into my browser, that's all I type, and I hit enter. What does the browser do? Well, it doesn't really know ahead of time whether foo.com speaks HTTPS or not. It could be just an HTTP-only site. So my browser is going to maybe try to connect to foo.com over HTTPS initially. And if that works, great. We're in good shape. But if the HTTPS connection to foo.com doesn't work for whatever reason, like the network doesn't deliver those packets, then my browser is going to fall back to regular HTTP. And then my connection to foo.com is susceptible to network attacks because there's no TLS protection at all. So this is what the paper was referring to with these SSL TLS stripping attacks, where an adversary that controls the network can just block HTTPS connections. And in some situations, like if a user just typed this set of characters in their browser and hit enter, the browser is going to fall back to HTTP. And then you effectively, that's what sort of the name refers to, you can actually strip these TLS connections by making the browser fall back to a non-TLS transport. Now, this doesn't work if you literally type in HTTPS foo.com. In that case, you're pretty explicit, and the browser shouldn't fall back to HTTP at all. Or if you clicked on a link to this URL, then there's no fallback. But in some situations, you might actually have this fallback, and that'll be unfortunate. Another situation where this fallback might show up is that if you normally click a link to HTTP foo.com, and foo.com's server just redirects to the HTTPS version of that site as the first thing it does. So that's pretty helpful, but it's not secure, because if you go to this link, an adversary can intercept this HTTP connection and prevent you from getting that redirect to the HTTPS site and keep you speaking HTTP all the time. That make sense? So that's one of the sort of things that certificates don't necessarily solve for us. So they solve man-in-the-middle attacks when you're directly going to one of these URLs, but they don't really help us decide whether the server speaks HTTPS in the first place. Another thing, I guess, that goes wrong, despite certs, is wrong names. So things like, PayPal.com with a 1. So colloquially, you might call these phishing attacks. So these are cases where the name technically matches as far as ASCII encodings is concerned, but the name doesn't really match as far as what the user is thinking they're seeing is concerned. So this is quite tricky to deal with. There were some attempts by CAs to have some plan for this, but didn't really work out. We can talk about that later. Does this make sense? Questions? All right. So another thing I wanted to mention that sort of does show up in practice sometimes is you might actually trick the CA to issue a bad cert for the adversary's public key. So here we were sort of talking, well, the adversary better not be a CA themselves. But another attack that has shown up in practice is an adversary might somehow fool the CA into issuing one of these certs to the adversary's public key under the wrong name. So this might be because of a bug in the CA, or because you've compromised the CA in some way, or the CA has some bad validation procedures, etc. Questions? Make sense so far? All right. So let's talk about, I guess, the kind of guarantee that this gives us in terms of the browser. So when we're using HTTPS in a browser, what does this actually translate to for us in terms of what we can sort of trust? And as you sort of hopefully are expecting by now, the main thing that HTTPS gives in terms of browser security is related to the host name we see in the URL. So there's some host name that's part of the URL that's visible to the user, and HTTPS really tries to connect the host name you're seeing to the server that you're talking to. So the connection, roughly, as we've been sort of sketching out, is the host name is really what the CA is going to authenticate in the certificate. And as a result, you can sort of convince yourself when you're when you're visiting an HTTPS page, this is really a page from that server. Assuming sort of none of these other sort of attacks like a compromised CA come into play, this is what HTTPS really guarantees to you. If you're seeing a web page that says Amazon.com at the top, HTTPS mostly tells you, yep, that's a page from Amazon.com. Now, of course, this doesn't guarantee many other things that you might actually care about. And in particular, for example, this doesn't really say anything about bugs in the JavaScript code that you might have gotten. So even though it's an HTTPS site, you could totally have bad or buggy JavaScript. Doesn't really say anything about forms or links that you might click on that page. So it might be that Amazon.com has some form that you fill out and submit somewhere. Doesn't actually guarantee that this form is necessarily going to be secure or that it's going to go to Amazon.com or anything about it. It's probably a form that Amazon.com's server sort of set up for you. So maybe this is what Amazon.com intended, but it's hard for you to conclude what's going to happen to data that you're going to enter on this page or links that you click. Another sort of big important exception to sort of HTTPS security is that really this guarantee applies to the sort of top level page, if you will. That's sort of an important caveat because there might be many parts of the page that are loaded from other origins. So in particular, there might be content delivery networks or other sort of places where JavaScript code is coming from into the page, or there might be elements like buttons, what have you, that are loaded from different servers. And just because the top level page is from Amazon.com doesn't mean that's where all the other pages are coming from. Again, that's probably Amazon.com's fault in some way sense if they cause you to load pages from other origins, but HTTPS alone doesn't really have anything to say about those kinds of restrictions. Make sense to some extent? Questions about what HTTPS is giving us? All right, hopefully clear enough. So the summary, I guess, is like it's really critical in HTTPS that, or the main guarantee we're getting is that we are getting a page from the server that we think we're connecting to. And just to sort of reinforce this point, extremely important, like this whole notion of name equals intent is critical to HTTPS, but doesn't actually always work out. So in HTTPS, this worked out well because the host name in the certificate that the CA validates is exactly the same as the host name in the URL bar that you're looking at. But there's a bunch of other protocols that use TLS and certificates that don't really have this property. And as a result, they're actually super susceptible to man-in-the-middle attacks. So just as one example, you guys are probably all using this. So here's a counter-example to how do you do name binding properly. And that's the 802.1x authentication for Wi-Fi networks. So if you have your laptop or cell phone right now connected to MIT Secure, then what actually happens is that your device, you might connect to MIT Secure, the wireless network SSID name, and MIT Secure requires you to log in with your username and password at MIT. What actually happens is that your laptop connects to the wireless access point, but it can't really talk to the internet yet before it authenticates. And to authenticate, it actually just opens a TLS connection to some login server. So when you connect to MIT Secure, there's some login server run by ISNT, and when your laptop or phone connects, they actually open a TLS connection to this server, and inside the TLS connection, you just send your MIT username and password to this server. Question is, if you're speaking TLS, you're going to get a certificate back from the server. What should you look for in that certificate? Like, how do you know? You should be sending your MIT password on that TLS connection. Any thoughts what your phone does with your password? Yeah? I'm sorry? Well, it does use TLS, so it's trying to encrypt it. But I think your answer of it just sends it is sort of right in that sort of this TLS, it does get a certificate from the server, but the client doesn't really know what to look for in the server. The server gets a certificate from some CA, and the CA might stick the name of the server into the certificate, but you're connecting to the name MIT Secure. The certificate authority has no idea if this is the right login server for MIT Secure. There might be actually lots of MIT Secure networks in the world. Like maybe in Germany, it's a perfectly popular name for networks. I don't know. So this is the problem in Wi-Fi networks. Right? There's not really a good connection between the name here and the name in the cert. The vulnerability that this creates for all of you guys is that your laptop will just willingly send your password over Wi-Fi to anyone that asks, roughly speaking. So it's fairly easy to create a fake wireless access point and ask your laptop to authenticate to a fake MIT secure network. It'll open this TLS connection and it'll send your password regardless of what the cert is. So that's quite damaging now. I don't know if people actually exploit this or not, but it takes quite a bit of effort on the client side to actually specify the names to expect in the cert. You can actually do it. Like on my laptop, I configure it to only, like, there's actually some name that MIT presents to you in the cert. It's like w92-radios-server.mit.edu or something like this. And you can make sure that your laptop will not send your password to random wireless devices. But it's not automatic. This is the problem. This is sort of the reason HTTPS got lucky, is that their goal of indicating the name you connect to connects very nicely to the kind of thing that a certificate authority can check about a public key. Sort of make sense? Questions? You seem puzzled. Well, I mean, here's a website I wrote. I mean, you can sort of blame me for it, right? But like, here's a non-HTTPS website. So they exist. I don't know, like if browsers didn't support HTTP, I would surely implement HTTPS myself. But I think it's a bit of a chicken egg problem. Like there's a bunch of little websites that don't matter very much that people implement with HTTP, partly because the browsers allow it. And because there's now many of them, the browsers have a hard time turning it off. And it's not so much that the browser, and it's maybe even stronger than this, many of these websites predated HTTPS to begin with. So they've been around, and the browsers have a hard time convincing them yet to all switch. I think the browser's long-term view on this point is that they will eventually discontinue HTTP. Or maybe eventually you'll have to like click an annoying dialog box saying, oh yeah, I'm allowing this really horrible HTTP site. And then probably we'll get more HTTP adoption and avoid these kind of downgrade attacks to HTTP. HTTPS adoption, I meant. Yeah. Make sense? A lot of many of you guys asked in questions like, why don't we upgrade faster? Like, how come we're stuck in this? It's really difficult to, like, the web is large and there's many servers and many browsers. It takes a while to coordinate them and get them all on board, much more so than in the kinds of systems we looked at in the first half of the class where it was one computer doing some isolation. And it's like, well, you can do whatever you want on your computer. So I think you see a lot of things that are sort of backwards compatible, constrained in these large network protocols without really a clear answer to why not. Like there's better alternatives for sure. The paper talks about many of them, but they're not deployed for various reasons. Yeah, question?
Just to clarify the name for this entity,
yeah.
is the issue that has come up is just because a network is called MIT secure doesn't mean that it has that the login server sends us the one login server that's real and secure that MIT secure and
Well, okay, so there's two logical sort of steps here. One is that just because you connect to this network doesn't mean anything about the server you talk to. This is just because this is an untrusted network, partly because it's wireless, partly because it goes over the internet and the back end, etc. So you'd like to use TLS and certificates to know that you're talking to the right entity. The thing that makes this doubly more difficult is that the certificate authority that you might ask to get a cert for this login server can attest to maybe the server name of the server, but not to the name of this wireless network that it's trying to serve for. So the name of this server might be like radios-server-1.mit.edu, but the laptop has no idea to expect that name of the server for this network. There's like this semantic gap between the network you want to connect to and the server that's backing that network. There's no such semantic gap in the web browser for HTTPS because the URL you see is what the certificate authority attests to. So, yeah, so a malicious MIT secure could let you connect to a different login server that has a cert name for attacker.com for all we care, and your phone wouldn't even blink. It would say, fine, yeah, that's maybe the right login server for MIT secure. Question? So there's many wireless authentication issues, and I think one issue that you bring up is that, some of these wireless protocols make it easy to mount denial of service attacks. Maybe your packets aren't well encrypted, or you could maybe guess the session key once you connect to a wireless network. That's all sort of, orthogonal to some extent. Indeed, there's denial of service attacks and some cryptographic weaknesses, but this is a fairly fundamental issue. Like, even if all those things were fixed, who do you give your password to when you connect? And that seems like an unavoidable question. If you want to just literally send an encrypted password to some server, you don't know which server, and there's nothing that can possibly help you unless you sort of somehow figure out not only the name of the network, but also like Mark Silas comes and says, well, guys, okay, to connect to MIT Secure, here's like the server name you need to type into your phone. You could do it, there's a field for it, but I imagine most people don't do it. All right. Other questions? All right. So let's talk a little bit about how certificate authorities bootstrap this whole database of names. So how do certificate authorities do validation? So the problem we're talking about here is we have some server like Amazon.com. It goes to the CA and tells the CA, hey, I want to register, Amazon.com, and here's my public key. Please give me a cert back. So the CA needs to do something to check. This is the real Amazon.com asking for a certificate. Otherwise, it's going to assign an arbitrary public key for Amazon.com. So it's important for the CA to do some kind of validation of these requests. And these days, basically, most CAs agree that the thing that every CA should do is what's called domain validation. And the goal for domain validation is to issue the certificate to the person or entity that has control of the domain. And you can think of various ad hoc ways that you might have the CA do this. So a fairly standard plan that used to be used by CAs is they would actually send an email to the owner of the domain. So you send this request to the CA says, oh, well, please wait a minute. Let me send an email to, admin@foo.com at Amazon, or at Amazon.com in our example, and ask the admin to click on a link to approve this request, if that's them asking for a certificate. These kinds of things. So this gives the CA some reason to believe this is the real Amazon.com asking for a certificate. One pretty significant thing that's happened since this paper came out is that CAs have standardized on a bunch of protocols for doing domain validation. It used to be, still is to some extent, this kind of ad hoc email owner kind of a thing. Nowadays, there's this protocol called ACME that is used by CAs, or by some CAs at least, to validate ownership of a domain. And ACME revolves around this notion of a challenge. So when a user comes to a CA and says, I want a certificate for this domain name with this public key, the CA tells the server or whoever requested this certificate, please satisfy the following challenge. And sort of the common things are, there's an HTTP ACME challenge, meaning that the CA will actually issue an HTTP, not HTTPS, regular HTTP request for some challenge file like Amazon.com / challenge.txt. And it tells the server, well, if you want a certificate for Amazon.com, please put the following random string into this file, challenge.txt, on your website. And if you can do it, it proves you're the person in control of Amazon.com. I'll give you a cert. Another example is maybe another style of challenge is a DNS challenge, which means that you have to create a DNS record, like acme challenge.amazon.com. And if the person requesting a certificate can create this DNS name, then the CA will try to look it up. If that lookup succeeds and has the random thing the CA gave to the client, then, well, clearly you're in control of this domain. I'll issue the certificate. So this is how the CA world seems to be standardizing on doing this domain validation, is in terms of these challenges that don't rely on encryption. Yeah?
How does the ACME protocol protect against
Okay, so the one question you have is, what prevents me from getting a certificate for all of MIT.edu this way? Well, one thing is I don't have the challenge.txt locker on web.mit.edu, for instance, so that's one answer. And also probably MIT's DNS system will prevent me from creating Acme or whatever, this funny name .mit.edu to respond to the DNS challenge. Slightly, not super satisfying perhaps answer for, some reserved names, and I don't have that reserved name. Well, that's why I'm going to have a hard time responding to this challenge. The other thing that's a little bit funny about this is that all these cryptographic certificates are being bootstrapped with no cryptographic security basis whatsoever. So all these bootstrapping protocols that the CA does to establish who gets a cert in the first place don't involve any crypto themselves. This is sort of what the lowest common denominator is that the CA world has boiled down to. So maybe the best way to think of CAs is that they give you a neutral perspective on the internet, because hopefully the CA server is running in a data center that's not subject to maybe man-in-the-middle attacks right at their network ISP level. And these certificates will help you if you're in some country or have an ISP that's doing a man-in-the-middle attack on you. Well, it's going to be better that you use a cert based on what the CA saw the network being. But it's not super, indeed, convincing, perhaps. So one thing that CAs try to do in order to mitigate the fact that they're doing these completely insecure ways to bootstrap certificates is they do what's called multi-perspective validation. So the idea there is that you might have some server that you're trying to validate, and it's all sort of connected to the internet, and here you have your CA that's trying to authenticate the server by sending it this HTTP challenge. Well, the idea is, let's try to at least probe from a couple of places in the internet. So maybe the CA has 3 data centers. So what's going to happen is that in order to issue a certificate, it's going to ask you to host this challenge on your website without HTTPS. And then it's going to request that challenge from 3 different places on the internet. So this way, if there's an attacker somewhere on the internet, as long as it's not right in front of the server you're trying to authenticate, then the CAs will see different answers, unless all of them are being man-in-the-middle. So that's sort of the thinking with multi-perspective validation, is that you get a more resilient way to probe a server without crypto that's resilient to some kinds of man-in-the-middle attacks. Hopefully this makes some sense. Questions? Yeah.
This server has a DNS name mapped to some IP address.
Yeah.
Is there a chance that the DNS will come to give you different IP address, and then the domain owner needs to synchronize all of the machines out of itself?
So, okay, your question is, suppose you have some complicated DNS setup where your name actually maps to many servers. Well, in that case, yeah, it's your problem as the domain owner. Well, if you have many machines that are behind your name, you gotta get all of them to serve this challenge for you. Or maybe do this DNS challenge instead, or something like this, indeed. Yeah. From an attacker's perspective, of course, any one of them will probably suffice. They'll just keep trying. But in order to make it reliable for you, the domain owner, you got to get all your machines on board. Yeah. All right. Any other questions about domain validation? That was like a slightly, good to know what a certificate means. The certificate basically means that, some CA probed directly over the internet, and that seems to be the result they got. So it's not really a much more in-depth statement about domain ownership or anything. But the nice thing is that CAs are actually coming to agreement on what a certificate means. It used to be that CAs were all different. Like some CAs would require you to fax in a fancy piece of paper with a letterhead of MIT and a signature from Raphael Reif, and others would just do email to admin at your domain. So now everything is sort of, standardized on the lowest common denominator, but nonetheless standardized is probably better than something more complicated. All right. So let's talk about some issues with certificates that we haven't covered yet. One of the more tricky cases with certificates has to do with revocation. And revocation is a problem with certificates because we have these long-lived signed messages. So these certificates that we've talked about, they have expiration dates, but the expiration dates are on the order of months or years. And as a result, if something changes about a site and their public key, the certificate that used to be out there is still valid. So, for example, if some adversary happens to steal our secret key from Amazon.com, that would be unfortunate. We would like the certificate to no longer be valid because this adversary can now impersonate Amazon.com. But, it's a signed message and it has an expiration date of next year, so it's still valid. The attacker can still impersonate Amazon.com for the next year. That seems pretty bad. Another example is actually domain transfers. What I mean by this is that, at some point, the paper, I think, gives us an example. Facebook actually bought the fb.com domain, but the previous owner of fb.com had a certificate for fb.com that was still valid for another year. So at this point, Facebook was using the domain for their site, but the previous owner of fb.com also had a certificate for fb.com that would have allowed the previous owner to impersonate Facebook, if need be, or if they wanted to. So this is a bit of a problem for certificates, to the extent that we want stronger guarantees for them, I suppose. And the problem is that, all these old certs are still valid, despite the fact that an adversary might have compromised the secret key. So there's a couple of ways that certificate authorities deal with this problem. The top-level plan is that CAs generally maintained some kind of a revocation list. And certificates, they'll just list them. Cert 1 has been revoked. Cert 5 has been revoked, etc. And the CA will just have a list of these guys. And the interaction of these revocation lists is twofold. One is that a certificate owner, some server, can come along and ask the CA to revoke a cert. Typically, if you can sign a message with the corresponding secret key of a certificate, you can probably ask the CA to revoke it because you've clearly demonstrated you own the private key that corresponds to the public key in the cert. And whoever you are, you're either the attacker or you're the real owner of the cert. Either way, you can ask for the cert to be revoked, and that's probably reasonable. So that's typically how this works. If you have the secret key corresponding to a cert, you can ask the CA to revoke your certificate. But then we actually need to tell the browsers, right? So the browser is going to be the entity that needs to know that some certificate is no longer valid. So we need some protocol by which the browser can query this list of revoked certificates from the CA. And here, there's not super wide agreement on what to do, or I guess, there's been slow convergence on some option we'll talk about, but none of the options are super satisfactory, if you will. Does the problem make sense of certificate revocation? Any questions about what's going on? Why we might care? Maybe as one bit of commentary, one reason why this certificate world seems so broken in some ways and yet not fixed is that I think to some extent people don't expect that much of it, partly because of that whole domain validation plan. These certificates aren't giving you some amazing level of security because you could probably mount various attacks on the certificate issuance process to begin with. So, there's some moderate level of security that certificates provide, and despite all these caveats, they're probably somewhat useful for average users. And if you needed stronger guarantees, certificates aren't going to provide them for a whole bunch of reasons. And that's why, maybe as a partial answer to why people aren't super excited or super quick to fix things. It doesn't matter that much, maybe. Yeah.
One thing about this is that all papers have given one or two examples of times that are actually broken. The Syrian government kind of little attack, and I think there was one or two other ones. But the buffer overflows you hear about multiple per year. So is this just particularly difficult to practically what
So your question is, okay, so for buffer overflows, it's every week you find new buffer overflow, and there's not that many examples of these CA attacks, is your question. And I think the answer is that you're right, and these certificate authorities are more difficult to compromise than some of the other attack vectors. So if your goal is to fool a user into going to the wrong site, it's probably much easier to trick them into going to paypal1.com than to get a fake cert. It's not like fake certs are necessarily that hard. You just have to like do some DNS injection attack, maybe on the CA issuance process. But it's even easier to do something else. That's why I think CAs aren't really the weakest point in security. They're actually okay. And a number of other things are even weaker. So that's why I think you don't see more CA attacks. Now, some systems really do have CA as the weakest point, and there is where you see attacks on CAs. Or sort of misissued certificates. That's probably, yeah, so maybe your sort of number of like one a year or a couple of a year is probably a reasonable estimate of how these attacks happen. They typically get used for much more serious things, like, for example, there were some attacks that issued certificates for signing of Windows updates. So this way you can send a fake Windows update to a Windows machine and it'll install code right then and there. Because it's signed by a key that has a sort of misissued cert claiming to be from Microsoft, for instance. So those kinds of attacks are very damaging, and in that case, the cert was the weakest point. But in the web context, certs are probably not the weakest point in many cases, and that's why not that big of a deal, maybe. Well, sometimes they are. I don't want to say certs are useless, but they're pretty good. All right, so let's talk about various ways that browsers might query this revocation list. So what are these revocation protocols? So the simplest one, and the one that's sort of was initially proposed for all these certs, is called a certificate revocation list, or CRL. And the design there is fairly simple. In every certificate that the CA issues, they embed a URL that you're supposed to query that's going to contain this whole list of certs from the CA. So the cert might have some URL, like, say, https, ca.com/bad.crl. So these are the list of revoked certificates. And then it's the browser's job to download this list of revoked certificates and then check if the cert that the browser is trying to use is in this CRL list or not. If the cert is in this list of bad certs, reject it. It's been revoked. Otherwise, accept it. So this was the initial plan. One downside of this plan is, of course, the bandwidth overhead. So every client now has to download this fairly large list of revoked certs, if ever there was a large number of revoked certs. So that ends up being a bit of a problem. That, and also, I guess this is maybe less of a fundamental issue, but turned out that most CAs didn't bother actually, they had these URLs, but they didn't actually work. Like for many CAs, you would request this URL, it would give a 404 back. This is before browsers took this seriously, but maybe 5 years ago, you probably would have been not universally seeing CRLs from CAs. So that's one way in which you might query the revocation list. It has some bandwidth problems, so that's a little bit unfortunate. Another way in which you might query the list of revoked certs is using this protocol called OCSP, for Online Certificate Status Protocol, or OCSP. So the design here is that the CA has this list of revoked certs, and the browser, when the browser gets a cert from some website, it actually sends the cert to the CA and asks, is the cert still good? And the CA sends back an answer, basically, yes, okay, or maybe it's been revoked, and it has to sign this whole thing in order to know that, that's an authentic response from the CA, of course. Does this protocol make sense in terms of what's going on? So is this a good or a bad plan? Any thoughts? Better? Worse? Why? Why is this better? Or why is this worse? Yeah. Yeah, so like if we're asking the CA anyway, what's the point? Like, why did we have a cert in the first place? Why didn't we just ask the CA, hey, I'm talking to Amazon.com, just give me their public key, man. So that's indeed, I think that's a valid way of thinking, and maybe one way in which this manifests itself is that the reason that we had the CA design in the first place, where the CA pre-signs these certificates, is that it got the CAs out of the critical path of connecting to a website. And with this OCSP protocol, you have to talk to the CA to decide if this is a good cert or not. So there's sort of two problems now. One is there's a latency overhead. Every time you want to connect to a site, now you go talk to a CA, and it's an extra round trip over the network. Another problem is that now the CA has to sign a lot of messages. These messages have to be signed because they have to be cryptographically secure. Otherwise, an adversary will fake an OK response. But now the CA has to have their private key online and signing messages all the time, and has to have a pretty beefy set of servers to sign this many messages for every website connection in the world at any time. So these are some serious problems for the CAs. So this ends up being not a super widely adopted solution for these reasons. Like, the browser vendors don't like it because it adds latency, and it slows down the user experience, and the CAs don't like it because they now have to have fairly heavy set of servers that are online all the time servicing these requests. Make sense? So the design that's mostly used these days is kind of a hybrid of OCSP, but it doesn't involve talking to the CA all the time. So the design that's typically used these days is called OCSP stapling. And you can sort of think of this as like really short-lived certificates. So the idea is that you have your browser, and you have your server that you want to talk to, and a CA behind the scenes, and it is the server's job to go talk to the CA periodically and give it the cert, and the CA, basically speaking this OCSP protocol, and the CA's job is to periodically, sort of, I guess every once in a while when the server asks, give back an OK or revoked status signed with the CA's private key. And this thing is going to also have an expiration date, but it's going to be valid for, I don't know, like 1 day or 1 week, something fairly short term. And then when the browser connects to a server, it's going to expect both a certificate from the CA, this is the usual thing that we've had before, plus this OCSP response that's been obtained by the server within the last day or within the last week. So this is what many websites do these days. The reason this gives you more security is that you get a more recent attestation from the CA about the validity of this public key to name mapping. So you get this response that's been signed within the last day or within the last week. So it's not immediately revoked, but within a day, your bad cert should be revoked on many browsers. And one interesting bit of sort of security here is that the browser needs to know to expect this thing. So an adversary shouldn't be able to use a stolen cert and just omit this OCSP response and say, oh, well, I didn't get this. Please just take the cert. No response that goes with it. The way this works out is that inside the cert, there's actually an extra field that basically says, please expect an OCSP stapled response. So the cert says the cert is only valid if it's accompanied by one of these fresher OCSP responses attached to it. So this is sort of the most recent, and I guess most practical revocation plan that's in deployment. Yeah, question?
Yeah, why don't you just issue?
Yeah, so I think looking at this way, it's like, well, why do we have two levels of certs? Exactly. So I think one reason is that, if you're designing things from scratch and you basically decided, hey, revocation isn't going to work, maybe we should just have short-lived certs, then yeah, of course. So this is partly an answer. It's like, well, we got here somehow and that's where we are. One slight reason why this might be a nice design is that the server doesn't need to do this whole challenge with the CA every day or every week, because the challenge might involve the administrator doing some steps and so on. The server can just present the certificate, and actually anyone, it actually doesn't matter to the CA that this is a real server at all. Anyone could have presented this cert. So in some ways, there's somewhat less authentication involved on a daily basis. So maybe that's a good thing in some way. So that's the difference. I don't want to argue this is like a great protocol, you have to do it this way. But that's one sort of minor technicality that differs between just super short-lived certs period and this sort of OCSP way of doing it. Make sense? Other questions? Yeah.
Anyone can prevent the search. Can't anyone therefore get the, oh no, it'll be timed with the first,
So you're worried. Okay, yeah. So everything has a public key in it, and these are all signed messages, so can't inject too bad of a thing here. Yeah, makes sense. All right. So let's talk a little bit about, I guess, another problem that sometimes occurs and what we can do about it, namely CA compromises. We talked about them a little bit in passing already, but just to be clear, sort of CA compromises are quite damaging if you're relying on these certificates to authenticate the server you're talking to, because indeed, if as an adversary I can break into some CA, I can sign a certificate that says, I'm Amazon.com or I'm Google.com or anything, and I can impersonate those sites. So what can we do to deal with this problem of compromised certificate authorities? And the answer is really there's not a huge or hugely satisfying answer, just to sort of, spell out the problem. Right, so if we have some bad guy that gets control of the CA and can get the secret key of the CA, then using the secret key, I can just mint any certs I want. I can just sign with the secret key any message of my choice. Google.com is, public key of the adversary. So to the extent that you're relying on certificate authorities, this is going to undermine your security guarantees. And there's sort of two answers to this. One is, if you're deploying something that's not a web application, you might want to have your own CA. So that's probably the best thing to do. I should say, like in this whole TLS or HTTPS ecosystem, probably one of the weaker links is these CAs. If you're talking about sort of programmatic applications that don't involve users that are susceptible to phishing. So if you're building some application that needs to use TLS, probably these CAs are going to be one of the weaker points in your design, so it's worth considering having a better plan for distributing keys, either using your own CA or maybe just hard coding some public keys or whatever makes sense for your application. That's going to be probably a meaningful security improvement. But that sort of only works out in the context of specific applications. What I'm thinking about is like maybe the WhatsApp app on my phone. It needs to connect to WhatsApp servers, and they probably aren't going to expect just like a straight up any certificate from any CA for WhatsApp.com. The app probably comes baked in with their own CA or their own public key, and even though they probably do use TLS behind the scenes, would be my guess. So that probably would be a good thing for WhatsApp to do. But if you're really sort of using CAs in the context of the web, sort of these public CA infrastructure, dealing with CA compromise is actually quite tricky because like fundamentally the CA is trusted. So if their secret key is compromised, it's hard to really do a whole lot of anything. There's one sort of clever idea that the paper briefly mentions that is actually one of the few things from this paper that did get deployed since the paper came out. Not necessarily because of the paper. I'm not saying the paper had sort of too much to do with it. But the paper talked about a whole bunch of ideas. Most of them didn't really work out. But certificate transparency is one thing that is fairly widely deployed today. So the idea with certificate transparency to deal with these compromised or misbehaving CAs is to have CAs basically record a log of all the certificates they're issuing. So even if the CA wants to issue these bad certificates, they're going to have to record those bad certificates in some audit log. So the idea is that if you have a server that asks a CA for a cert, so here's, some register operation, then the CA, as part of issuing the certificate, is going to have to talk to an entity called the certificate transparency log. And the certificate transparency log is a server that maintains some kind of an append-only data structure that has all the certs that have ever been issued in the world. It's like a pretty large data structure. And the CA needs to send the cert to the CT log, and then the CT log is going to stick the certificate in its log and send back a receipt of sorts, some kind of pointer into this log with some cryptographic hash commitment to where the cert appears. And the idea is then now the cert given to the server includes this receipt. And at least in theory, browsers can ask servers to produce these receipts. So the only search maybe a browser would accept is a cert that comes with this receipt from the server, which convinces the browser that not only is this a cert signed by one of the supposedly trusted CAs, but even if that CA got compromised, at least here's a receipt that that cert was logged in that data structure. So even if this is a bad cert, someone out there is going to see it and do something about it eventually. That's sort of the thinking behind certificate transparency. So these receipts you can think of as signed messages from these CT logs with some kind of a Merkle tree hash pointer. This is sort of the design or sort of the ideal of how CT logs work. In practice, browsers don't really check or demand these receipts. And the reason is sort of the same as OCSP, which is that the browsers don't want to incur extra latency of having to talk to the CT log server, validate this receipt, and all that stuff. So instead, what this sort of boils down to is mostly a way for other participants, like browser vendors, to have some kind of an audit process that periodically downloads all the things from the CT log and looks for funny entries. So that is one thing you might be able to do. So you can actually look at these things. So let me see if I can pull it up here, crt.sh, so I can look for, like, this is crt.sh, is like some site for one of these CT logs. You can look through all the entries there. Might take a while to search just because it's a giant data structure, but we can see if it finds anything. Maybe that's too long of a string. Maybe there's too many C-cell certificates. Let me search for, oh yeah, okay. So if I search for my web server name, that's easier to find. Like here's all the copies of my certificate that have been logged into the CT log since 2013, I guess is when this log started. So it's been logging certs for quite a while, and it has copies of all the certs that are issued for my server. And you can actually search for, other things as well, of course. Like we can search for all C-cell certificates. Maybe it'll come back eventually before the lecture finishes. Oh yeah, there they are. So you can actually find all kinds of certificates that have been issued for ccell.mit.edu. They're all public now because of the CT log, and you can sort of audit them. It's not clear what exactly you would do. Like, how do you know it's a good one or not? It's just a bunch of certs. You don't know if they were asked whether the public key inside that cert is from some adversary or not. But I think one reason why this CT infrastructure has been deployed is that it gives the browsers a way to pin down the CA if there's something funny going on. And you can say, well, you issued this cert. Let's dig down and figure out, oh, that's a bad cert. We'll kick you out of our root list of trusted CAs, for example. So in a couple of times when it's happened that browser vendors have actually kicked out CAs from the list of trusted CAs in the browser, it's sort of used these CRT logs or CT logs to really argue, well, you issued this cert. We know exactly which certs you issued. These are all bad. You're not playing by the rules. So it's more a point of leverage for browser vendors and CAs rather than necessarily a client-facing mechanism. But nonetheless, this is one thing that might be helpful in the case of a CA compromise because we have this hopefully authentic list of all the certs issued by different certificate authorities. Does this make sense? Questions about this whole certificate transparency scheme? So I didn't really describe exactly how these receipts are constructed and what they look like. There's some fancier crypto and hashing going on behind the scenes. But sort of the idea is to just sort of log. That seems like the best we can do in the case of these compromises. And I should say there are multiple of these CT logs out there. Each one of them sort of maintains this list of certs. And most browser vendors like Chrome require CAs to send all their certs to one of these CT logs in order for them to remain in the list of trusted certs in the browser. Make sense? Questions about CA compromises, these CT logs, etc.? All right. So that's probably all I had to tell you guys about certificates. It's sort of a complicated situation, and we've ended up here through a bunch of incremental steps, but provides okay security these days in terms of making sure you're talking to the right name server of the network. There's a whole bunch of things like CT logs and OCSP stapling that are kind of cool ideas. But as we talked about, they're probably not the weakest point of security in at least web security. So that's why they're sort of slow to improve from their current situation, perhaps. All right. I guess that's it. If there's any questions, feel free to come up afterwards. But I see you guys on Thursday. We'll have a guest lecture from someone that's been doing sort of security in industry. Will be an interesting perspective.